All right, we're going to talk about section 10.6, turbulent flow, and the Moody diagram in chapter 10, flow and conduits. So we are right here in this portion of the chapter, and this is a very important section. It allows us to determine the friction factor or if certain information is given, we can find the Reynolds number, and so it's a very, very important graph in fluid mechanics and conduits. So let's flip forward to section 10.6 and start off here. So here we are. We're talking about turbulent flow now in this particular section. And we are remembering from earlier in the chapter that the Reynolds number, as applied to the diameter of the pipe, if it's greater than or equal to 3,000, we have turbulent flow. And we know that turbulent flow is chaotic and unsteady, and there's a high level of mixing in the flow. And this is important because turbulent flow really equals most flow in conduits. So this is something that we really need to be able to deal with as we move forward. And we've noted before that these are going to be empirical, we're going to use empirical equations or equations that have been derived through experiments rather than derive equations for the most part, because turbulent flow is too difficult to describe, primarily because it's chaotic. It's too difficult to describe with analytical solutions to equations. So this is the velocity distribution here is typically given by what's called a power law. And so we've got R0, the radius of the conduit, minus R, the distance from the center. And we have this is going to be given as a to the power of m. And this table down here from the book shows that these exponents for the power law, these have all been derived for different regimes within the flow at different Reynolds numbers. And so you can see that this exponent is 1 over 6 for this particular Reynolds number, and then 1 over 6.6 and so forth, kind of decreasing as we go up. And also we have a ratio here of the maximum velocity, which we need in here, to the mean velocity. So if we're able to determine the mean velocity, then we can find U max and then plug that in, plug in m, and find the velocity as a function of the distance from the center of the pipe. Now, the other approach is to fall back on the equations that we saw from last chapter, and in particular, the most relevant equation is that for the logarithmic volume profile or region of the flow. And so we have that here, and of course we've got the shear velocity, which is again equal to the shear stress over the density, square root of that. So we've got a couple of different ways to derive the flow. These, again, coming from empirical formulas or experiments that were done at various Reynolds numbers, and this equation here being one that was derived from our boundary layer development in chapter 9. The book doesn't do this, but it does state that this equation can be found from basically determining looking at an equation for the flow, the volumetric flow. If you start from this equation and plug in, the book basically says we do the integration, do a bunch of algebra, and we end up with this equation. And so we have an equation here for F that we can solve. We can solve for F in terms of the Reynolds number. What's interesting is this is for a smooth wall. This was determined by Prandtl for pipes with smooth walls. And that could be a useful, that is a useful formula, but a lot of times we have pipes that have rough surfaces, and so Prandtl's student, this guy Nikoradze, who was a graduate student of Prandtl's, actually did experiments where he glued inside the pipe. He meticulously went and glued in little grains of sand onto the inside of the pipe, uniform onto the inside of the pipe wall, and then sent some flow through and determined basically a relative roughness pi group. This is, you can see that if this is the size, basically the K sub s is called the sand roughness height. So it's an indication of what the heights of these are. So if we looked at the pipe on end, you'd get this little bump here, these little bumps from these sand grains being in there. The Ks would be some characteristic height of these sand grains. And if you take that over the diameter of the pipe, d, that gives you a dimensionless group here, Ks over d, which is called the relative roughness. So Nikoradze did all these experiments under the direction of Prandtl, and basically these were the results of those experiments shown in this figure from the book. So what we have here at the bottom, we have the Reynolds number. It's just the velocity times the diameter divided by the kinematic viscosity normally. We've seen this before, and here's what they're calling the resistance coefficient or the friction factor. We can see the laminar regime here for values less than about 2,000. Looks like they've gone a little bit over here to bigger values, but this is the laminar region, and again we know that this is 64. This particular formula is derived from 64 divided by the Reynolds number. And Prandtl's number, Prandtl's equation, which we just saw back here, this equation right here, in fact, describes this line right here. You can see that this is the smooth wall tube, and then all these other lines here were experiments that his graduate student did, depending on the roughness of the inside of the pipe. And so here are the data for when the roughness is large, we get higher friction factors, which makes total sense to us. And when the relative roughness gets small down here, for most of the time, we're actually equaling that of a smooth wall. So we have to get to pretty high Reynolds numbers in order to start to deviate for the low relative roughness. We have to get to a pretty high Reynolds number, pretty high velocity or pretty large diameter pipe in order to start deviating from the smooth pipe. So I think it all makes sense, physical sense. This is a table from the book which basically outlines the effects of the wall roughness for different regimes. We've got the laminar regime here. We know that F depends both on the relative roughness, but it's independent of the wall roughness. So we know, we go back to this equation, we can see that there's all the dots of different types lie right along this line, and there's no Ks over D does not appear in this equation for the friction factor. So then for Reynolds numbers greater than 3,000, turbulent flow, but basically low relative roughness, we're going to have that F is going to depend on the Reynolds number, and it's also going to be independent of the wall roughness. That is again the smooth tube profile, which is right along here, as I mentioned. You can see all the values from the different types of experiments lie right along this line. A bunch of different symbols that lie along this line until the Reynolds numbers get high enough and they start to deviate. Then, in the transitional flow region, Reynolds number has to be greater than 3,000, but for moderate values of the relative roughness factor here, we have F depending on Reynolds number and depending on the relative roughness factor. Um, and those would be these values out here. We can see that it's depending quite a bit on the relative roughness factors. And then by the time we get to high Reynolds numbers and really large roughnesses, F is independent of the Reynolds number, but it depends on the wall roughness. So once we get up to here, up to this flow, we can see that it's fairly independent of Reynolds number now. But it does depend out here. These lines are flat. They're not depending on the friction factor, but they are depending on the Reynolds number. I'm sorry, I take that back. They depend on the roughness, but the friction factors and are very different for the different roughnesses. So that just kind of gives you an idea of when we look at this chart, kind of these different regions of those experiments done by Prandtl and Nicoradze. And I just love the image of the poor graduate student, gluing these little sand grains into these pipes over and over and over again, different size sand grains, and having to run those experiments over and over again. But it certainly was a valuable dissertation. So this all gets boiled down into this Moody diagram, which is very similar to the experimental results we were just showing. Here's the Reynolds number down here at the bottom. So obviously this is a value of 2,000 here. So this is the laminar flow regime. Again, this is 64 divided by the Reynolds number applied to the diameter of the pipe. And then there's a transition region. And then where you start in the turbulent regime is going to depend on your relative roughness. So these blue lines are constant relative roughness. So we can see that when we get to high roughness, there's very little variation. From here on over to the right, there's basically no variation with Reynolds number, and there's just a slight variation over here. For very low relative roughness values here, there's quite, it looks like a smooth pipe, so there's quite a large variation of friction factor changes depending on the Reynolds number. So the friction factors are higher for lower Reynolds number, and as the Reynolds number gets larger and larger and larger, the friction factor decreases. So if we're given a set of information here, say the relative roughness or the Reynolds number, we can go and put a point on here and we can determine the friction factor. If we have the friction factor, of course, we can go and we can find the pump head, or I'm sorry, not the pump head, the pipe, the head loss is what I'm looking for, because we know that equals this equation right here. So remember, this is the reason why we're trying to find F, so that we can find head loss. If we know the head loss, this is a little difficult to see, but if we know the head loss, this equation right here comes from Darcy's law. We can plug that in and find out which of these black lines we're on. And for instance, if we know the friction factor, we'd be able to find the Reynolds number, or if we knew the Reynolds number, we'd be able to find the friction factor. So this table can be used, if we already know the head loss, we can use the table to find other characteristics of the pipe if we know, say, for instance, the flow in the pipe or the Reynolds number. So these are just another table in the section 10.6, gives us the relative roughness for various types of pipe materials. Glass and plastic, like PVC, are obviously very smooth, and so KS is going to be, we're going to follow that sloping line down on the friction factor in the Moody diagram. And then we've got copper, it's quite smooth, all the way up to values of like concrete, which are have very, very high KS values, as sand grain roughness values. And so if we know this value, read this value off this table, and we know the diameter of the pipe, we can find the relative roughness. So if we knew, say, the relative roughness from that, we could choose which value here we needed, and then we can go to the appropriate Reynolds number and pick off the value of the friction factor. and then determine the head loss in the pipe. So one other thing is if we are using a computer, we might not want to be going back and forth to refer to the Moody diagram all the time and having to read this chart. This is an empirical equation that fits all those lines on that on the Moody diagram. Basically, you can use this equation to reconstruct the Moody diagram. It predicts, it's called the Swami-Jain formula, and it predicts the friction factors to within 3% of all of those values on the Moody diagram. So we can go and use the Swami-Jain formula and calculate all these numbers given the inputs. And so you can see that it's taking as input the relative roughness, Ks over d, which is a dimensionless quantity, and it's taking the Reynolds number to the 0.9th power. This is all dimensionless, and this number is dimensionless, so f is a dimensionless number as well, as it should be. So that's it. We'll get some practice in class on how to use and read the Moody diagram to solve various problems in turbulent flow in conduits. Thank you.